Hello and welcome to Ott in Math. In this edition of Ott in Math, we're going to talk about changing bases and exponential equations. Right, so let's move on. Right, so we said that one of the benefits of logs was to be able to solve for an unknown value of x as an exponent. Here's a case where we know 7 squared is 49 and 7 to the third power is equal to 343. So we know x has to be somewhere between 2 and 3. But we don't know exactly what that value is. So we're going to use change of base formula in order to solve for x. And let me show you how it works. Right, so the first thing you want to do is you want to rewrite the exponential equation as a log equation. So log base 7 of 95 is equal to x. Then you're going to apply the change of base formula, which says that I can change the base of any log as long as I take the log of the number divided by the log of the base to figure out what the value of x is. So that's what I want you to do right now. I want you to take the log of 95 and then divide it by the log of common log of 7. And I'll pause for a moment while you do that with your calculators. All right, you should get a value that's approximately 2.34. Now let's check to make sure that that value is correct. You're going to take 7 to the power of the value that you just calculated, common log of 95 divided by common log of 7. Take 7, it's approximately 2.34, and you should end up with 95 in your calculator. Right, so this also works. Remember I said it was the change of base formula allowed you to change it to any base, and we use the common log or a base of 10 because the values are pre-programmed into your calculator, and you can use those values in the calculator to use the change of base formula to solve for x. Another value that's programmed into your calculator is when you have the natural log or base of e. So you can go ahead and try natural log of 95 divided by natural log of 7. You're going to come up again with 2.34 approximately. Take 7 to the power of 2.34, and you should again end up with 95. So we can see that change of base formula works something like this: log base 5 of 8, same as common log of 8 divided by common log of 5. And we can see that log base c of a will result in log base b of a over log base b of c. We can change the base to any base as long as it's the same base value. And by the way, it doesn't have to be 10 or e. It can be 7, or it can be 10, or it could be 3 if you want. Whatever works for you in order to solve whatever is required of you. You can see that in this case I was able to simplify the numerator only by using a log of the base of 7, in this case log base 3 of 49. Changing the base to 7 and rewriting this as log base 7 of 49 over log base 7 of 3, which allowed me to simplify the numerator in this case, which doesn't really get me anywhere. But just as an example, there might be certain parameters in which it will be helpful for you to simplify at least this portion of the expression to an integer. In this case, that's what we did. Just as an example, again, you don't need to convert the base to 10 or e, but commonly that's done just because the values are calculated in your calculator. So let's take a log base 5 of 7. We can rewrite that as log 7 over log of 5. And that equals 1.21. And similarly, we can use base of e, natural log of 7 over natural log of 5, to get a value of 1.21, the same value. All right, so we're going to move on. These are just some more examples for you. All right, so we talked before, I believe in chapter 5.6, about solving log equations. We talked about equating logs using the property of equality. We talked about exponentiating logs. We didn't really cover special product patterns that much. Now we're going to talk about using the change of base formula, taking the log of each side to solve log equations. All right, so this is how it works. So we're confronted with an unknown value as an exponent. We're going to write the equation down. 8 to the x is equal to 30. We're going to rewrite now in log form. Log base 8 of 30 is equal to x. Use the change of base formula, log 30 over log 8, or natural log 30 over natural log 8. And we'll end up getting 1.636 approximately as a value for the unknown exponent of x. All right, so I want you to take a moment and solve for x in this case. I'll pause for a moment. All right, log using change of base formula, first rewriting in log form, log base 3 of 12 is equal to x. Log 12 over log 3 is equal to x. X is equal to 2.26. And you can verify that by taking 3 to the power of 2.26, and you should get approximately 12 for that value. All right, so I want you to, you're going to need to use a calculator for these. I want you to solve for x in this case. I'm going to pause for a moment. All right, so the first one, rewrite in log form. Natural log of 18 is equal to x. X is equal to 2.8. It says 2.89. Let me just double check. Okay, so 2.89 is correct. I was just checking to make sure it wasn't a 4. 4 to the x is equal to 20. We write this as log base 4 of 20 is equal to x. Change of base formula, log 20 over log 4 is 2.16. 8 to the x is equal to the cube root of 5. Rewrite this as log base 8 of 5 to the 1/3 is equal to x. I can rewrite this as log base 5 to the 1/3 over log of 5 to the 1/3 over log of 8. Additionally, I can rewrite this as 1/3 times log 5 over log 8. You'll get the same answer, 0.26. And then the last one, I'm going to rewrite e to the x is equal to 1 over 0.01, which is 100. E to the x is equal to 100. Natural log of 100 is equal to x. And so the natural log of 100 is equal to 4.61. All right, so let's move on to another problem for you. We're going to take an equation here, and you're going to use change of base in order to solve for x. I'm going to let you struggle with this for a moment, and then we're going to come back and solve it. So please pause for a moment and try to work this out on your own. All right, so you can see that this is really a quadratic with some exponential spice to it, I guess I'll say. So 2 to the x squared minus 2 to the x minus 6 is equal to 0. We can factor it like a quadratic. 2 to the x minus 3 times 2 to the x plus 2 is equal to 0. We're going to factor, use our zero product property to solve. 2 to the x is equal to 3, or 2 to the x is equal to negative 2. And you recall when we were talking about exponential functions, domain and range, you know that in this case, the value for y can never be less than 0. Regardless of what value you substitute in for x, you always get a positive result for y. So this is an extraneous solution. I'm left with 2 to the x is equal to 3. Change of base formula, change it to log form, log base 2 of 3 is equal to x. Now x ends up being 1.58, and that is your solution. All right, so you can try another one. Let's see if you can tackle this one. That'll be it for today. 3 to the power of 2x plus 1 minus 7 times 3 to the x plus 2 is equal to 0. You can see that we've created some type of a pattern with the quadratic function. Let's see if you can factor this one. All right, so I can rewrite this as 3 to the 2x times 3 minus 7 times 3 to the x plus 2. So here's a trick here. You need to use your properties of exponents in order to separate the base into 3 to the 2x times 3 to the first power, which, as you recall, is 3 to the 2x plus 1, which I can rewrite as 3 times 3 to the x squared minus 7 times 3 to the x plus 2. Now we're in a similar situation that we were in before with the prior example. 3 times 3 to the x minus 1 times 3 to the x minus 2, factoring these. Using my zero product property to solve, 3 times 3 to the x minus 1 is equal to 0. 3 to the x is equal to 1/3. Change of base formula, log base 3 of 1/3 is equal to x. X ends up being equal to negative 1. And then 3 to the x is equal to 2. Change the base formula. Log base 3 of 2. Change the base formula, log of 2 divided by log of 3, and you should get 0.631 for a value for x. All right, that's it for Chapter 5.7, Solving Exponential and Log Equations. In this edition of Math, that completes Chapter 5 on exponents and logs.